Welcome back to our flipped chemistry classroom, and today we are continuing our conversation about chemical reactions and equations by talking about reaction types. So the reason that we talk about reaction types is by classifying reactions into their types, we can find patterns, and those patterns are going to allow us to predict the products of reactions. So by being able to recognize what type of a reaction it is by looking at the reactants, then we're going to be able to predict what the products are going to be. So we'll start by talking about something called double replacement reactions. And so double replacement reactions are those where you have two compounds, usually two ionic compounds, but they could be an acid and a base. So you have two compounds and they exchange their ions. And this happens in an aqueous solution. So this means it happens when it's dissolved in water and it forms two new compounds. And so we can write this kind of generic equation for these where we have AX plus BY yields AY plus BX. And you can see where this anion Y has swapped places with X. And so we have two ionic compounds or two compounds to begin with, and we have two new compounds, different ones that have swapped their ions in the product. So when we have these, usually one of the compounds is a precipitate or an insoluble gas that bubbles out of solution, or in the case of a neutralization reaction, a molecular compound like water. So let's take a look at, so there's two kind of within double replacement reactions, we can classify these into two types of reactions. And we're going to talk about precipitation reactions and neutralization reactions. And a precipitation reaction is a double replacement reaction where one of those two new compounds is insoluble. So we would have two aqueous solutions, a solution of AX and a solution of BY. And when we mix them, we get a new solution, and that contains one usually soluble compound. In this case, we have AY, and one insoluble compound, which in this case is the BX. So here's our example. If we mix a solution of sodium chloride, so a solution of table salt, with a solution of silver nitrate, then we're going to get a solution that contains sodium nitrate, but the silver chloride is going to precipitate out. So we're going to mix two clear solutions, and we're going to wind up with a solution that has a white powder sitting on the bottom of it, and that white powder is silver chloride. So that's a precipitation reaction. We took two aqueous solutions, combined them, wound up with one aqueous solution and a solid. The two ionic compounds have simply switched partners. So sodium was partnered up with chlorine, silver was partnered up with nitrate. Now the sodium's with nitrate and the silver's with the chloride. The other common type of a double replacement reaction is what we call a neutralization reaction or an acid-base reaction. And when we have a neutralization reaction, we always have an acid and a base reacting, and that neutralization reaction will always form water and a salt. And a salt, remember, in chemistry just means any ionic compound. So here's our generic equation. We have HA, that represents our acid, plus BOH, that represents our base. And when they come together, they form liquid water and a salt, which would be the B, the cation from the base, and A, the anion from the acid. So here's our example. We have hydrochloric acid coming together with barium hydroxide, and that's going to form water and barium chloride. Now, you chose this example on purpose because it's very common for students to get mixed up with this kind of a problem. And they see this H and they see this OH2 and they put something like HOH2. And you forget that in order for barium to be neutral in its compound with chloride, we need two chlorides. And so we need the two here. That gives us two hydrogen ions and two hydroxide ions. And that's going to make two molecules of water. So make sure when you write these that you're always paying attention and you're expecting to see a product that is water and salt, not necessarily table salt, but a salt, an ionic compound, and make sure that that ionic compound is neutral. Okay, so moving away from double replacement reactions. So we had two kinds of double replacement reactions. We had precipitation and neutralization. Most of our other reactions are what we call redox reactions or reduction oxidation reactions. And in reduction oxidation reactions, electrons are transferred, and they're usually transferred from a metal to a non-metal, but sometimes they might be transferred from one metal to another. So the rest of the reactions we're going to talk about all fall under this category of redox reactions. So we have single replacement reactions, and single replacement reactions, like double replacement reactions, one element gets replaced. But the difference is that in a single replacement reaction, an element is replacing an ion in a compound, or an element is replacing an atom in a molecule. So rather than having two things which simply swap partners, we have one thing that comes in and replaces. We are always going to wind up with a single replacement reaction making one compound and an element. It starts with a compound and an element, and it ends with a different compound and a different element. So we can have replacement of metals by another metal. We have an example of that here with A plus BX. And we get AX plus B. We know this must be the metal because this is the cation. This is the first element in the compound. It can also be the replacement of hydrogen in water by a metal. It can be the replacement of hydrogen in an acid by a metal, or it can be the replacement of a halogen by a more active halogen. And that would probably be what we have an example of here with our BX plus Y yields By plus X. Here you can see that the anion is being replaced rather than the cation. Now, when we talk about single replacement reactions, just because we put an element and a compound together does not mean that every single one of these reactions is going to happen. And so when we talk about single replacement reactions, we're going to talk about something called an activity series. And when we talk about the activity series, we mean that the more active the metal is, so the higher it is on this list, the more active it is, and that means that it is going to replace another metal if it is above the metal it is trying to replace. So any of these metals from lithium all the way down to lead will actually replace hydrogen in an acid. So if I add an acid to any of these metals from lithium all the way down to lead, then we will actually get a compound that is that metal and the anion from the acid and hydrogen gas. And metals from sodium up, these ones from sodium all the way up to lithium, are so active they'll actually replace hydrogen in water. And in solutions that contain any of these metals in a salt, so if I have a solution of nickel 2 chloride and I put in a chunk of zinc, it will replace the nickel in the nickel 2 chloride and we'll wind up with solid nickel and zinc 2 chloride. So we do have to have them be more active in order to replace. And metals will always replace metals. They will not replace the anion. With halogens, it's a little bit easier because it's all about their placement on the periodic table. Halogens can replace other halogens in compounds if they're higher than the halogen that they're trying to replace. So fluorine will replace chlorine, but bromine won't replace chlorine because bromine is lower on the periodic table. It's less active. So when we look at this example, if I have sodium chloride and I introduce fluorine gas, I will get sodium fluoride and chlorine gas. The fluorine will replace the chloride. But if I have magnesium chloride and I introduce bromine, there will not be a reaction. So the activity series can be used to determine whether or not a single replacement reaction will happen. Our next category of type of reaction is what we call a synthesis reaction or a combination reaction. And this is when two or more substances combine and they form one new compound. So the defining characteristic of a synthesis reaction is that there's only one product. Okay, so we might have two elements, as we see in this generic equation, coming together to make a compound, or we could have two compounds coming together to make a compound, but there will only be one product. And some examples of this, most elements will react with oxygen or sulfur. So if we have calcium and we expose it to oxygen, we'll get calcium oxide. So we started with two elements and we wound up with a compound. Metals and halogens. So sodium with chlorine gas is going to make sodium chloride. Here again, we have two elements coming together to make a compound. But we can also have two compounds. So when we have water and sodium oxide, we will wind up with sodium hydroxide. So again, we have multiple compounds coming together to make only one compound. So that's a synthesis reaction. It produces one product. The opposite of a synthesis reaction is a decomposition reaction. So a decomposition reaction is characterized by the fact that it starts with a single compound and it produces two or more simpler substances. It, again, does not necessarily go back to the elements, although it can. So our generic equation is AX yields A plus X. We can see very often decomposition of binary compounds. So when we decompose water, we get hydrogen and oxygen. Those metal carbonates are going to break up into metal oxides and carbon dioxide gas. Our metal hydroxides will also break up into metal oxides, but with water. Metal chlorates will break apart and we'll wind up with metal chlorides and oxygen gas. And then our oxyacids will break up into different components. This particular one breaks up into carbon dioxide and water. These are almost always redox reactions. Certainly, if we go from one compound to pure elements, they will definitely be redox reactions. But a decomposition reaction is characterized by the fact that we start with one compound and we wind up with more than one. And then combustion reactions. So combustion reactions, we have a substance combining with oxygen. It releases a large amount of energy in the form of light and heat. So the less common example would be when reactive elements combine with oxygen. Those can always be considered to be combustion reactions. So if we have phosphorus and we combine it with oxygen, we will get tetraphosphorus decoxide. This will give off a lot of light and heat. In fact, this is one of the reactions that happens in the tip of a match. And it is a pretty simple and straightforward reaction that gives off a lot of heat and energy. This is also a synthesis reaction. This is also a redox reaction. The other and kind of more typical form of a combustion reaction is the burning of a hydrocarbon. So a hydrocarbon is made up of carbon, hydrogen, and occasionally oxygen. So this would be things like natural gas, wood, gasoline, and anytime we burn a hydrocarbon, anytime we have combustion of a hydrocarbon, it will always make carbon dioxide and water. So again, it's relatively easy to predict the reactions. So we have 6 reaction types. When we classify reactions into their types, we can find patterns that are going to help us predict the products of the reaction. So those reaction types, we have 2 kinds of double replacement reactions. We have precipitation reactions that make a solid and an aqueous solution from 2 aqueous solutions. We have neutralization reactions where we combine an acid and a base and we get water and a salt. And then we have our different kinds of redox reactions. We have single replacement where an element replaces an ion or an atom in a compound. We have synthesis, where two compounds combine to form one compound. We have decomposition, where one compound breaks apart into smaller, simpler compounds. And we have combustion, where something combines with oxygen and gives off heat and light. So that's it for today. As always, I look forward to seeing you in class. And if you have any questions, let me know.